We present hysteresis compensation of a flexible continuum manipulator using RGBD sensing and temporal convolution network. The main contributions in this paper are as follows. We use the pseudo-rigid body representation to solve the forward kinematics. The coordinate systems and the DH parameters can be shown in the figure and table. This figure shows the configuration of the degrees of freedom and the geometric relationship of cable length variation during the bending of hinges. Through this relationship, a cable driving equation can be derived. These are videos that control the proposed manipulator based on the cable driving equation mentioned in the previous page. And now, here is the flowchart of the hysteresis compensation of proposed manipulator. We compensate the hysteresis in 3 phases. For the first, data collection. The center position of the markers is captured with an RGBD sensing. The position and orientation of the end effector and base are calculated through 7 fiduciary markers. After obtaining transformation matrix base to end effector, the inverse kinematics is calculated to obtain the physical joint configuration. We make random trajectory through interpolation procedure and did the data collection as you can see in the video. We can see the hysteresis through figure A and B. In B, the hysteresis curve is very complicated and non-linear, making it difficult to use analytic model compensation. Next, the modeling the hysteresis. For modeling the hysteresis, we employ 2 approaches using 4 architectures. As you can see in the both figures, the TCN with sequence length 80 exhibit the superior performance for both forward and inverse approaches. Finally, the hysteresis compensation algorithm. The algorithm utilizes the TCN forward and inverse model. It takes the desired joint angle as input and computes the command joint angle, which can align the robot with the desired joint angle. We validate the performance of the proposed hysteresis compensation algorithm on unseen 3 trajectories, which is random, circle, and zigzag patterns. The calibrated controller has better performance in tracking the desired trajectory as shown in figure ACE, and it has lower tracking errors and standard deviation as shown in figure BDF. There are notable reductions in mean position and orientation errors in task space. In addition, the hysteresis compensation controller shows significant improvement in joint space. Thank you for your attention on our project.